Welcome to our introduction about our own galaxy, the Milky Way Galaxy. Our galaxy is made of around 400 billion suns, 400 billion stars like our Sun. Of course, not all of them are exactly like our Sun. We already learned that there is a variation that you can see all over the HR diagram. As you recall, a lot of small and reddish stars and fewer blue giant stars. These are all making hydrogen into helium, and that's their source of fuel, whereas we also have stars that are off the main sequence as well. These are the 400 billion stars that are scattered around 100,000 light years in space. That's the size of our Milky Way Galaxy. Light from one end take 100,000 years to reach the other end of our Milky Way Galaxy. In today's lecture, we will see how these have been found. In front of you is a star chart that I left for you to use with Lab 3. In this image, you can see our sky map or sky chart. Please recall that this is describing the night sky as they are in July in the early evening. Of course, the map is an inverted negative image. Also, it represents the dome of the sky. The map is of the whole sky, so if you have a laptop, for example, then the south is at the bottom, but you cannot see with your eyes anything more than about half the map. In order to see what's going on to the north, you have to take your laptop, turn it upside down, and face north. And then the half map that is in that direction is what you will see between your zenith, the point above your head, and the northern sky. And the same thing with the east and the west. Now, you notice that on this sky map there is a blue stripe. That blue stripe is not quite in the middle. It's a little slanted, and you can see that it's a tad to the east. You may be able to see it if the sky is very dark, if there are no clouds, and if you are far away from city lights. That's the Milky Way. That is our own galaxy. Now think about our own galaxy as a giant pancake, a very large pancake. Now stick your head into the pancake. Assume your head made a circular gap. And now imagine that you stuck your head into a pancake and there's a circular gap, not even in the middle, and you're looking around you. What you will see is a stripe. Towards the center, where the pancake may be a bit thicker, you would see a little bit thicker stripe. Of course, that galaxy of ours is not exactly along the ecliptic or along any other line. It's a different line, and that's basically the plane of the galaxy. As you can see, it is tilted relative to other celestial lines. Now, with the naked eye, the Milky Way looks very faint, very fuzzy. It was Galileo Galilei, the same guy that saw the phases of Venus and their different sizes, that aimed a telescope first at the Milky Way, where he saw what he described as multitudes of stars. This structure in the sky before Galileo was actually described by the Australian Aborigines first as the backbone of the sky, basically a very faint bone of the sky that's holding the dome of the sky up. The Greeks imagined it to be something that the gods left, basically a trail of milk, hence galaxy, which in Greek has to do with the Milky Way. Galactic, think about it as in lactic acid or as in lactose intolerance, has to do with milk, and that was the case until Galileo. Between the 1600s, Galileo's time, and the early 20th century, there was no support for the notion that we live in a region of the universe that we now call a galaxy. Philosopher Immanuel Kant called galaxies island universes, but he had no clue about context, content, number, and distances. For that, we needed to understand stars. Here again is in the HR diagram, our means of understanding stars a bit better. Now click to see the HR diagram of clusters of stars, with some stars that are just starting to veer off the main sequence. That means that this is a cluster of stars where the age is now more than a few million years, so all the fat guys that burn their energy quickly and die off are no longer on the HR diagram. Click again and you'll see the HR diagram for a different kind of stars called globular clusters. Cluster of stars called globular clusters. These would be clusters that have only about 1 million stars. One such cluster, if you would look a couple of slides back, is in the constellation of Hercules and is called M13, and that's exactly above our heads, which means in the middle of the chart. So those clusters of million stars, okay, not hundreds of billions, only millions of stars, have a very, very interesting thing about them. That is, stars turned off the main sequence, and we have very, very few stars that are blue or anywhere in the O, B, A, and even F part of the spectrum. So, in this cluster, is it old, young, or intermediate in age? Again, remember, the turn-off means that very fat, chubby stars that live their lives are not there anymore. They exploded, became supernovae, neutron stars, black holes, white dwarfs. So again, young, old, or intermediate? Obviously, very old. One more thing, obviously very far away, because once we look at those stars and actually look at that cluster M13, for example, in Hercules, we'll find out that they're way fainter. You take the total light, divide by the million stars that's in them, so every single star is way fainter than the equivalent main sequence stars that are placed at 32 light years or 10 parsecs away, which is the normal for the HR diagram. So they're mighty far away. They're actually thousands of light years away. Recall, nearby stars are a few light years away. So thousands of light years is now a fairly large distance. Not millions, but thousands of light years. Remember that for the next slide. Near the beginning of the 20th century, at around 1915, an American astronomer named Shapley used the HR diagrams and also some nifty tool called variable stars to measure distances to those globular clusters. He also looked to see what their distribution was in the sky. He made a 3D map of the galaxy, and we simplify it here to a 2D map. The region around which those clusters are more concentrated is near the constellation Sagittarius the Archer. That's in your sky chart to the south, in a constellation that looks a little bit like a teapot and is just between Scorpius and the Gemini constellation. Capricorn. The reason the clusters hover around that region is that there is an egg yolk in the middle of the pancake. That is, there is a region very rich in stars near the center of the galaxy. Of our 400 billion stars, lots and lots of them are near the center. Let's look near the center with more modern techniques. We cannot see anything in visible light towards the very center of the galaxy near Sagittarius A. That's because it's mostly obscured by dust. It can be seen in radio, infrared, X-ray, and gamma. In the book, they go very nicely through all of them. Here I emphasize just the radio and the X and gamma ray. In the first radio picture towards the center of the galaxy, we see that it is a very active region with many supernova remnants and star-creating regions, and that can be told from the spectra and from other effects that are very common for supernovae and active regions. For example, the speed of ejecta that can be measured with Doppler shifts. Now this supports the notion that we just said, that there is a huge density of stars towards the center of our galaxy, towards Sagittarius A. Also, the interstellar gas there is a bit thicker. As a result, if there's any object like a neutron star or black hole, it will surely emit some light. It doesn't emit as much light at this time as we expected, but we have indirect evidence that there is a black hole that is about 1 million or 10 million times the mass of the Sun lurking in that region right next to Sagittarius A. The X and gamma rays pictures that you click and see would support that.